Are we running? All right. Welcome to event number 2, live broadcast in the Robotic Vision MOOC. As I talked about last time, what we're going to do in this live event is actually bring it to you from our robotics lab. I'm going to introduce you to some of the people who are doing robotics here, talk to them about how they got into robotics, and look at some other robots that we have right here in the lab. To make this broadcast work, I've got Andrew holding a USB web camera. Behind him is Jason, who's carrying a laptop, running Google Hangouts, and a very long Ethernet cable going off to the wall. This is kind of a pretty fraught technological setup, but we hope that it will work. So first off, I want to introduce my colleague, Matthew Dunmabin. Come on over, Matt. This is Matt, and he's going to talk to us about some of the work he's been doing with robotic boats. But first off, Matt, tell us about your educational background and how you got into robotics.
Yeah, sure, Peter. Well, so I started a long time ago in aerospace engineering, actually, and sort of, even though I did aerospace engineering, I was more interested in the modeling and the control and dynamics of the problems. So after I finished my degree, I actually went into computer modeling of road trains, and these are big, for those that don't know, big 6-trailer trucks that drive around outback Australia.
Yeah, I've seen them.
And so I went into the design and the dynamics of those. And then I decided to do my PhD, which was in control. Following my PhD, I actually started working for CSIRO. It's a national research organisation where I got into mining robotics. And after a few years of mining robotics, where it's primarily field robotics, so it's also path planning, control, vision systems, all sorts of the whole gamut there. I really got into sort of what can I do to protect the environment, and I started sort of to stream what we call environmental robotics. And these are designed to operate in the environment to do large-scale environmental monitoring, help report on the state of the environment.
So instead of people going out there and measuring stuff, we've got robots out there instead.
And what I've found, I hang around mostly with actually ecologists and marine scientists, and that's where I spend most of my days. And how do I make tools better for them in the environment? So
your customers are not engineers or geeks?
No.
Okay.
So these things have to work 24/7, they have to be out there collecting real data that they're going to use to make potentially policy decisions on. So, yeah, we've been trying very hard to make systems that will stay out there. Particularly, my focus is around the marine and aquatic domain, but I'm now moving into terrestrial as well. So, yeah, we have some examples here of some of the work that we've been doing in the aquatic domain.
Brilliant. Tell us about the yellow boat.
Yes, so this is one of our new projects. So, as I mentioned, we're really interested in persistent autonomy within the environment. So we've developed 4 of these robot boats to start with, and we're going to, well, they live on a water storage normally, just going around. They've got 3G connection to the real world, and they just persistently just go around day and night collecting different types of data. So they usually have a camera on top. We're taking the camera off there here. They've got different payloads. So this is a gas sampling payload.
Come on in.
Yeah, sorry, guys. Come on in. So this is a gas sampling payload. So it actually measures methane gas emitting from the water storage. And we can actually map the dynamics. Now, one thing I didn't mention is a reason why we do this is mostly data is sort of gets interesting at nighttime or in significant events where we're actually not allowed to put people out there. And this is where robots really start to make sense. So these are quite simple robots, solar powered. Underneath we have pods for batteries and electronics on either side, so we can put those on, and we can swap out the payload. So this is a gas sampling payload. We also have a payload for water sampling. We have one for doing bathymetry, so getting the underwater topography. We have camera systems for measuring what we call the riparian zone, so that's the edges around the lakes and things like that. So and this data is either stored or processed on board. But from a robotics perspective, it's really interesting because we have to consider we've got very low very minimal solar panel area. So how do we manage the trade-off between where we want to go, how much power we have, and also the keeping systems alive and all those sorts of things. So it's quite an interesting problem. Now, one of the cool things that we're doing with this is we're actually going to make these live to researchers around the world. So these will be online. So we've got the portal up. It just hasn't been released yet. Where we've got a water storage. It's closed to the public in Queensland here, where we're broadcasting from. And researchers can bid for some time using these robotic platforms to collect data, and they can then run their model. So this is more for ecologists, marine scientists, that type of thing. And using this system, they can get a username, password from me. They have access for a week or two, and they can collect data and then build up their models and then report back. The whole idea is around sharing what they learnt. How do we compare models that work in the northern hemisphere to the southern hemisphere? All these type of questions that can start to be answered with robotic systems. So yeah.
Fantastic, Matt. Do you want to tell us about this yellow submarine over here?
Yeah, so another sort of tool in our arsenal for environmental monitoring is underwater vehicles. So probably a lot of groups online might have some of these. Very interesting devices. This one's actually used for measuring water quality. So it's a submarine, self-propelled, endurance up to about 8 hours. It has what we call an acoustic Doppler velocity log, just here. Now this allows you to measure your speed over the ground, but also this has an upward-looking one as well, so we can actually get the water current profile as we're going through the environment. It has a side-scan sonar for building up terrain maps, GPS and everything in the tail when you're at the surface. Obviously, that's one of the big challenges when you're underwater is you don't have GPS, so you need other modes of localization. And on the front, we have this, you might not be able to see from the angle there, the water quality probe, and this measures things like blue-green algae, pH, turbidity, those type of things. So this is all logged on board, geo-referenced. We get the data back and we build up models. So we've done things like mapped desalination plants that are sort of releasing to the environment while they're operational. And this is something you couldn't do with manned operations. It's too dangerous, but we can put these robots out and actually collect that type of data.
All right, Matt, thank you very much. So also in the sort of the maritime robot space is this much larger robotic boat. I introduce Ricky Lamont. Come on over, Ricky. So Ricky is a student here at QUT, and he worked in a team to put this boat into an international competition. So Ricky, I'm going to ask you the standard question. Tell us about your educational background. What are you studying, and how did you get into robotics?
So I'm studying mechatronics at the moment. I'm in my 4th year, and I major in robotics. I guess my interest in robotics started when I was a wee little kid, and I first got to visit the Kennedy Space Center. I saw the Mars rovers on display there, and I don't know, I always wanted to do it after I saw those. Throughout my degree, I've done a combination of sort of mechanical engineering, a lot of electronics, and sort of computer science as well. That's given me sort of a broad understanding of all the robotic problems that I could face once I finished my degree.
Okay, and then you signed up to work with Matt on the Maritime Robot Challenge.
Yeah, so I was the team captain for the Maritime Robot Challenge. What the challenge was 15 university teams from all around the world came together in Singapore last year. They're all given one of these platforms. So there was no motors, no sensory packets, just a floating base for us to work on. And we were given the task of turning this boat into a robot. So up the front, we fitted a rather substantial sensor package. We got scanning lidars, cameras for computer vision. Although it's missing, there were GPS and IMU systems. In the center here, we have our brain. There's just an off-the-shelf computer in here that does all our computation. Then at the back, all the control systems and safety systems. This was an amazing opportunity for us. It gave us as students the chance to work on a real-world, full-scale robotic system. We got to learn a lot of the challenges and pitfalls of working on robots in the field. One thing that we did learn really quickly is that out on the field, you don't have all the resources you necessarily have to work with you have in the lab. And there was a lot of really challenging problem-solving tasks to keep things working out on water storages and things like that.
So what, a lot of late nights and a lot of improvisation?
There were many late nights, and I have not fun memories of frantically trying to pull things together in a grassy field next to a lake to try and keep things working so I could get testing done.
Fantastic. Thanks, Ricky. Thank you. All right, so the next kind of robotics that we're doing rather a lot of here at QUT is in the agricultural space. So we're looking at agricultural robotics. And when we started this journey in agricultural robotics, started probably early 2011, we got a bunch of funding to do agricultural robotics, and we need to get going pretty quickly. You can't just go and buy an agricultural robot off the shelf. And at that point in time, we didn't have the resources to be able to build a robot from scratch. So what we did is we built this vehicle we built this vehicle here. So this is an off-the-shelf electric-powered vehicle made by John Deere. It's called a Gator. It's a little utility vehicle, and you often see them around parks, carrying plants and dirt and whatever. Really handy little vehicle. And we paid a company some money to turn this machine into a robot. So although it's got seats and it's got pedals and it's got a steering wheel, we made it drive by wire. So the computers in these cabinets here are able to tell the vehicle how fast to drive and what rate it should be turning at. So that's only part of the business of making a robot, right? Is to make it so that the machine can be controlled by a computer. The more important bit is the perceptual system. How does the vehicle know where it is? And for the particular task that we were looking at, it's weed spraying. So we wanted to be able to follow rows of crops. So to do that, rather than rely on ultra accurate GPS, we wanted to rely on vision. So if you come around the front here, you can see the primary sensors for this robot are these two cameras here. So this is a stereo camera pair. They're on quite a long baseline, which is important because that gives us the ability to get pretty accurate depth resolution as this vehicle is driving along. So it uses these two cameras to build up a three-dimensional profile of the ground in front of it, which is the actual ground of the field, but also the plants that are sticking up from that ground. So it's quite complex environment in front of the robot. It's not a simple plane. Now, in order to be productive, a robot's got to be able to work 24/7, and cameras clearly going to be problematic at night when it's dark, and particularly even worse when there's no moon. So we built, one of our students built this LED-based illuminator. So this is a big array of super bright Cree LEDs, and it's pulsed and it outputs an enormous amount of light. So this is effectively an ultra bright headlight for this robot that allows it to work at nighttime. A bunch of other sensors on this as well. We have some inertial sensors which tell us about the attitude of the robot on the field, roll, pitch, and yaw angles, and its accelerations. We've got a very high accuracy GPS system on the top here. We don't actually use this to guide our robot, but we use this as what we call a ground truth. So if we're trying to build a low-cost vision and inertial-based navigation system for our robot, how do we know how well it actually performs? So we cross-reference the performance where we think it is using our low-cost nav system and compare it with where we are using highly expensive but highly accurate GPS system. So that's how we can tell the performance of the navigation system we created. And two of our PhD students spent basically 3 years working on all of the systems on board this robot. So they did a lot of the electronics and they did all of the software, and they developed some amazing algorithms for navigating this vehicle through a field and also for doing collision avoidance. And I think last week I showed a tiny snippet of a video showing this particular robot avoiding somebody standing in the field. So this was a way that we got started in agricultural robotics. But what we learned from doing that was that this particular vehicle, the mechanical platform, is not really very suitable for the task. It doesn't have very much ground clearance, and that causes a lot of problems. It's also not very good when it's very hot, and we had a lot of overheating problems with this platform. So we learned a lot from building this, and then what you should do really in every project, build a prototype, you learn a lot, and you throw it away, and all you go forward with is what you learnt. And so you take those learnings forward and you create the next iteration of your system. And so at that point then that we got a bunch of additional funding into the group here at QUT, and we were able to ramp up what we're doing in agricultural robotics. And now it's time for me to introduce Ray Russell. Ray's over here. Hey, Ray.
Hi, guys.
So we recruited Ray to come and help out with building our next generation of robots. And you can tell Ray's not from around here. He's from Pittsburgh. That's where we grabbed him from. Ray, tell us a bit about your background and how you got into robotics.
So ironically, I'm an aerospace engineer as well, like Matt. So, but I don't think that's...
So is Jonathan.
Yeah, and Jonathan as well. So we have three engineers, which isn't too much of a stretch because you think, I mean, they're both fields of dreamers, right? Yeah. Aerospace engineers dreaming to go to the stars, and robotics dream about making the world a better place to live. So yeah. I don't think it's too, I think it's not too Ironic that they both end up in the same place. But so I started out as an aerospace engineer for about 20 years, ended up in the consulting line of work, just moving around, solving problems at all these large aerospace companies. And I ended up at Carnegie Science Center in Pittsburgh doing a one-year exhibit on flight. You know, and they wanted an
so
aerospace.
you're building something for a museum.
Yeah, and they wanted an aerospace engineer on the staff to make sure that the exhibit on flight was technically correct, because there was all sorts of different exhibits. There were wind tunnels and things like that. Concurrently, because all science centers and museums never have enough money because they're nonprofits, they said, we're doing an exhibit on robotics. Is there any way you could like manage both of them? And I said, yeah, I mean, airplanes, robots, there's gears, pulleys, bolts. And that got my foot in the robotics industry in Pittsburgh. And it just happened to be that Carnegie Mellon was in Pittsburgh. That's one of the world's large robotic universities.
Absolutely.
I started doing work for them as a consultant. And then one day they came in and said, the contracts are getting too big. You're going to have to form a company. So I started my own robotics company. And we ended up building kits to modify gators into robots.
Yes,
and,
you did.
You know, one thing led to another, and here I am.
So that was our first encounter with Ray. Is we hired. It was his company that came out and converted our gator. That's Ray's first introduction to Brisbane.
Right. Right.
So Ray, tell me about this drawing behind and why it's important.
So I guess I came down in December of 2012, thinking that was probably going to be my last visit to Australia, like a world, you know, like a lifetime dream to come to Australia. And then a year later, I get a call out of the blue saying, hey, you know, the gator's been a very good success. We've got some more funding. Would you like to come down and work some more? And I said, yeah, you want like 2 or 3 weeks? And they said, no, like 2 or 3 years. And I was in a place in my career and my business and my life, I thought, you know, I'd like to take a crack at that. But what really got me interested is when they sent me this. So my experience as a business owner has been robotics is having a hard time getting out there in the commercial world because everything looks like a high school science experiment. It's hard for the investors to see like what the final product would be. So this time the group kind of did a little different thing where they actually brought an industrial designer in before they brought the engineers in, and they did a bunch of design conceptual concepts. And this is what they sent me in an email, and my response was, I'll be down on the next airplane. So rather than seeing a high school experiment, you see almost like what a finished vehicle would be. So investors come in, because ultimately we want these things to be out in the hands of the users. When investors come in and they see it like this, they can see that, you know, that's a finished product, that's not just a collection of parts. I call them Frankenstein experiments. So that's how I ended up here. And after about a year, that picture is sitting here in three-dimensional form now. We got all the covers off of it because we're installing electronics in the frames right now, but it is as close to that picture as you can get from a concept to a finished product.
So Ray, you want to take us around the machine? What are the key features?
Yeah. So what you mentioned, Peter, we had issues with height clearance getting over the crop. So you know we got it up much higher now. So it's got about almost 1 meter clearance. We had trouble with heat because in Australia it gets very hot. So we've gone with water-cooled motors on this one. We went with a simple platform, just what they call differential steering. It's just got 2 motors up front. You know, you rotate them differentially to steer. You rotate them together to go forward and backwards. So it's a pretty simple design.
Go around and see the motors.
Probably the most important thing is that what the farming robotics, most of the effort has been basically just robotizing large vehicles that are already man-driven. This has kind of been a shift away from that sort of thinking in rather than just replicating a human in a large vehicle, why don't we replace that human-driven large vehicle with like 10 smaller vehicles? This solves like 2 problems. One of them is now that you don't have a single point of failure. If you're a farmer, you have one large $250,000 tractor, it goes down, you're done until that tractor's fixed. With these, if you have 10 robots, one of them is out of commission, then you got 9 that are out there doing the work of to help out on that one that's down for repair. The other thing is there's issues in Australia because of the lack of rainfall. You get high soil compaction here because the vehicles have gotten so big and heavy. You have a high wind come along, your topsoil's gone. The plants have a hard time getting up through that compressed soil, so dropping the vehicle weights down quite a bit is going to improve that soil compaction issues that they have here. So we've got the mechanical design done right now. Jason's over there working on installing the brain. I always call my job, I'm like Igor in the Frankenstein story. I go out and find the dead bodies, I dig them up, stitch them together, but then it takes the smart guys like Peter and Jason here, the electronic and software guys, to bring them to life. So that's where we're at right now.
All right. Thanks very much, Ray. Thank you. All right, so that's some of the robotics activity here at QT. If we look around the lab, we'll see a few other little robots. Dwayne Corner's just behind Andrew. There's a little tiny mobile robot there. Now I'm behind the camera guys on the floor there. A little mobile robot platform. Another one over here. This is a clear path husky. Matthew's been doing some work. He's been looking at inspecting what goes on in forests. And we've also had this running along beaches doing some inspections. So this is a really rugged four-wheel drive differential steer mobile robot platform. And we built this tower, this stalk, which we can put various kinds of sensors on, 3D lasers, stereo heads, and whatever. So this is kind of it really for the sort of currently active robotic projects here at QUT. So what I might do is maybe have a look at some questions on notice. I got at least one question here on notice from my pocket. So maybe we just go and find a comfortable place to sit. Or maybe I just prop myself up against this robot here, and we'll take this one. So this is from Paul Farrier, and his question. He's got two questions. I want to ask multi-part questions. He says, what were the most challenging vision or robotic problems that I've had to solve during my career? There's actually been quite a few. At one point, as with Matthew, we did a lot of work in mining robotics, and one of the kind of mining machines that we wanted to automate was what we call a dragline excavator. That's a huge machine like a rotating crane, and it lifts about 100 tons of dirt at a time up in a bucket. And this bucket is suspended on cable. So you can imagine you've got the boom of the machine, which swings around like this, and there's a bucket suspended on cables. And we wanted to know the lateral sway of this bucket with respect to the plane of the boom. And to do that, we thought, okay, this is easy. We'll put cameras up here and we'll look down. And that was challenging because you look down and there's a big bucket full of dirt against a background of dirt. And the whole machine's moving. If the camera was stationary in space, that would have been easy, but the whole camera's moving as well. So that was a very challenging problem. And like the agriculture robot, this system had to work night and day. So there's a lot of challenges in that. Another really challenging one that we worked on was in an underground mining application. So in an underground mine, you have these long horizontal tunnels, and they drill radial holes out from the tunnel, and they pump explosive into those holes so they can fracture the rock and bring it down and take it away, because that's your product. And so we were tasked to create a robot that would be able to guide a hose, which it pumps explosive into these holes, which had been pre-drilled. So we didn't know where they were, we had to find them. And so we're underground in a very, very dark tunnel, and trying to find the mouths of these holes which had been pre-drilled. And the rock surface is not smooth. It's quite ragged, and that was a very, very challenging problem. Problems with lighting and shadows and reflections and things like that. So that was really challenging. From just getting the scene well lit, so that you can then find what's a hole and what's not a hole. And in a few other projects, the challenges have been of a kind of different nature, and they've been really around size and weight. When we first started doing work on flying robots back in the very early 2000s, we were not able to carry very much payload. So we were counting every single gram that we put on the helicopter. So we needed to get really, really lightweight cameras that had sufficient resolution and sufficient frame rate to do the job required. So there's some of the challenges in the robotic vision front. So Paul's second question is, he says he has a computer science background, great, and would love to transition to the robotics industry sometime soon. So what would improve his chances of getting into the industry beyond successfully completing these two courses? To do these courses, I think, is going to give you a lot of really useful and relevant knowledge. If you could take sort of university level courses for credit, that's probably going to be a bit more convincing than certificates of completion from a MOOC. But hopefully in the future, MOOC credentials get to be taken a bit more seriously. But the other thing I think that's really important for somebody who wants to get into robotics is start building stuff, right? So get yourself some Raspberry Pis, and get yourself some motors and some sensors and some cameras, and just build stuff. And I think that's what's probably common to everybody who works here. I think we're all so passionate about robotics that you know, it's not just a day job. I think we want to do it all the time. So yeah, start building things, get those practical skills, and I think if you can, you know, go to a potential employer in the robotics industry and talk not just about your educational credentials, but about your passion for the field and the sort of things that you've created, I think that would be pretty invaluable. So Obi, are there any more questions? No more questions coming in? So we might wrap the session up at that point. If you've got any more questions, post them on the discussion forum. We can either answer them on the forum or I'll pick them up and talk through them in the next live event. So thanks very much for your time and for listening. Until next time, goodbye.